Hello everybody. In this video, we will explore the Copernican Revolution and learn how Copernicus, Brahe, and Kepler challenged the geocentric model. As we discussed previously, the Greeks developed the geocentric model to explain the motion of celestial objects. This model was used throughout the medieval period without being challenged. This all changed in the 1500s when Nicolaus Copernicus, a Polish mathematician and astronomer, proposed a new model where the Sun was at the center of the solar system. There is evidence that the ancient Greeks had considered a heliocentric model. Using geometry, Aristarchus of Samos estimated that the Sun was at least 20 times further than the Moon and that it must be much bigger than Earth. Since one of the justifications for the immobility of Earth is its large size, Aristarchus concluded that the Sun could not move as well because it's even bigger than Earth. But his ideas were largely dismissed, perhaps because it was considered too radical, given deeply ingrained notions about uniform circular motion and the immobility of the planet. Copernicus' model revived the heliocentric system of Aristarchus. His model proposed that the Sun, not the Earth, is at the center of the solar system, that Earth rotates around its axis, producing the daily motions of celestial bodies, and that Earth revolves or orbits around the Sun, producing those annual motions. But because of his conservative nature, Copernicus was reluctant to divulge his ideas. His book, Revolutions of the Heavenly Spheres, was published on the year of his death, 1543. The book was published in Latin, it was long and difficult to read, and it was not widely circulated. One problem with Copernicus' model is that it still recycled many Aristotelian ideas. He still used circles upon circles or epicycles to try to get better matches to data and to reproduce the non-uniform speeds of the planets. Despite some flaws, his model provided a natural way to measure the distances between the planets and the Sun. For the inferior planets, it used the geometry of maximum elongation. For the superior planets, it measured the time from opposition to quadrature. The distances from the Sun are only measured relative to the Earth-Sun distance, also known as astronomical unit. The problem was that neither Copernicus nor anybody else at the time knew how big the Earth-Sun distance was. There were many religious and scientific objections to Copernicus' model. Among the strongest religious critics was Martin Luther, who wrote scathing commentary about Copernicus and his idea. There were also scientific objections, mostly from Aristotelian scholars. Among the pointiest objections was the fact that both the rotational and orbital motion require Earth to move around the Sun at very high speeds. Also, there was no observational evidence of revolution or rotation. And finally, predictions of planetary motions made by the heliocentric model were not a significant improvement on the calculations based on the geocentric model. Many scholars pointed to the fact that stellar parallax was not observed. Today, we know that the reason stellar parallax were not observed was that stars are much farther than people thought at the time. Stellar parallax does exist, but it is too small to measure. especially at that time. This is the same reason why stars do not change in brightness as Earth revolves around the Sun. One of Copernicus' followers was Tycho Brahe, a Danish astronomer and brilliant instrument builder. Despite his admiration for Copernicus as a mathematician, Tycho did not like the idea of a moving Earth. However, in November of 1572, he noticed a new bright star in the constellation of Cassiopeia. We know today it was a supernova explosion. He made detailed measurements of the phenomenon over the next 16 months. Seeing such a change in the celestial realm was in serious contradiction to the Aristotelian ideal of celestial perfection. He decided to investigate, and for the next few decades collected an impressive amount of detailed measurements of planetary and star positions. Brahe used a giant quadrant to measure planetary positions in detail. But because he still could not detect stellar parallax, he continued to think that Earth was at the center of the solar system. He developed a hybrid system that used concepts and ideas from both the geocentric and the heliocentric systems. In his model, Earth is also at the center. The Moon and the Sun orbit Earth, but the other planets all orbit the Sun. Brahe's model was not taken seriously, but he collected an impressive amount of data and compiled the best astronomical database in Europe at the time, which were archived at his famous Uraniborg Observatory. The database contained 20 years of precise planetary data and the positions of almost 800 stars. But the definitive blow to the geocentric model was his demonstration that the center of motion of the Great Comet of 1577 was the Sun and not the Earth. Brahe left Denmark in 1597. 2 years later, he was appointed the imperial mathematician in Prague and hired Johannes Kepler as his assistant. He died in 1601 and Kepler took his place, using Brahe's extensive and detailed observations to discover the truth about planetary motion. Kepler had a genius for analyzing data and began immediately working on Mars, which was the key to unlocking the secrets of planetary motion. We'll discuss Kepler's astronomical revolution in the next video. In summary, we learned that Copernicus created a sun-centered model, but was reluctant to divulge his ideas, which received both religious and scientific objections. Tycho provided the data needed to improve Copernicus' model and created a model of its own, a hybrid model, using geocentric and heliocentric concepts. Tycho hired Kepler as his assistant, and using Tycho's database, Kepler found a model that would revolutionize astronomy. Thank you for watching, and I see you in the next video.